We're going to continue on into chapter 7 to keep taking a look at what's going on with our rational numbers. Here we want to start talking about operations on decimals. So we're going to start doing arithmetic with our decimals. If I want to add decimals, it is very important that you use the decimal itself to line up the values. So if you notice when I write this vertically, I lined up my values exactly. So I do 6 plus 3 is 9, 1 plus 7 is 8, and 2 plus 1 is 3. Then I have the visual representation because as you're presenting this to your students for the first time, this is going to really help them quantify what they're doing. If I'm adding decimals and I'm looking at the horizontal view, we can break it down by place value. However, most students are going to find that this is not friendly. So we can do the same operation here and say 6 plus 3, 1 plus 7, and 2 plus 1. We don't have to break it down into place value here. When I'm multiplying decimals, we do have a slightly different rule. So when you're multiplying decimals, let's say these two here, 6.2 times 1.43, you're going to want to write them vertically. You don't have to line the decimal up because we don't worry about the decimal until the very end. So I'm going to do my 2 times 3, 2 times 4, 2 times 1. Then I'm going to do my 6 times 3, 6 times 4, 6 times 1. So I get 286 plus 858. I'm going to add those together, and that gives me 8866. Then I'm going to count the number of digits behind the decimal between the top and the bottom. So I have 1, 2, 3 digits, which means my answer has 3 digits behind the decimal. So that's how you're going to determine how many numbers are behind a decimal. In part B, you'll notice I've done the same thing. I've entered them in. I've completed the multiplication already. Now in part C, I've done the same thing, and there's only one value behind the decimal. So my answer only has one value. Scientific notation is what we use to represent very, very large or very, very small numbers. So for instance, this very large number is going to be the distance that light travels in 1 year. I typically don't write out that many zeros. Typically, we're going to express that as 5.872 times 10 to the 12th power. So that's typically what we're going to do because we don't want to show all of those zeros, especially since the zeros don't have a lot of meaning other than place value for a very large number. The mass of an electron is another one. I've got all these zeros in front of the decimal. So what I have to do with the scientific notation is only one value is allowed in front of the decimal. So if I look at this one, if I started back here, I'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 spaces to move the decimal point to where I only have one value in front. Here, I'm going to have 4 spaces to move the decimal point until I have only one value in front. In scientific notation, a positive number is written as the product of a number greater than or equal to 1 and less than or equal to 10. To write a negative number, we treat the number like it's a positive number, and then we're just putting the negative in front. When you have something like this, 10 to the negative 4, that does not mean the number is negative itself. That means the number is just small. So if I look at each of the following and I write them into scientific notation, I'm going to move the decimal point until there's only one value. Here I have to move the decimal point 8 times to get to where there's only one value in front of it. Here I'm moving it 5 times, but I'm going to the right, and because I'm going to the right, it's going to be a negative 5. In part C, I'm going to have 8.37 times 10 to the 1 because I only had to move the decimal place one time. And in part D, I would move it 7 times to get into the 1, between the 1 and the 0 here, and I put the negative in the front, not in the exponent, in the front. So if we're moving from scientific notation to standard numerals, I'm going to take this decimal place here behind the 6, and I'm going to move it 5 places to the left because it's negative. If I'm here, I'm going to take the decimal place between the 3 and 1 and move it 7 to the right, which makes a big number, which we should follow that pattern. Negative exponents should be very small, positive exponents are going to be pretty big. And then in part C, I'm just going to ignore that negative, and I'm just going to move the decimal place 4 places to the right. A scientific notation on your calculator is typically indicated with the EE button. If I want to do scientific notation, you don't actually type the times 10. If you do that, a lot of times it will do it incorrectly. So you would enter it as 5.2 in the EE button and the exponent here, so 16. So 5.2 times 10 to the 16th is entered as 5.2 EE 16. And the same follows for the next one, and you're going to use your calculator for these problems. You're not going to do them by hand. Now, if I want to divide decimals, that's going to be a little bit of a building block off of multiplying decimals. When I divide decimals, I'm going to put 4 into 128.6. I'm going to say, well, 4 goes into 12 3 times, 4 goes into 8 2 times, and then I have the 6 that I have to deal with. So I'm going to be able to keep adding those zeros behind it because 4 goes into 6 one time with a remainder of 2. So I have to annex that 0. So this is the process that most of us have learned to complete the division of decimals. The decimal stays lined up and we keep going until we don't have a remainder. So when the divisor is not a whole number, like here, we can get to a whole number by expressing the quotient as a fraction. So basically, if you look at A and B, I move the decimal 2 places to the right in front of the division symbol and inside. Do you see that? I moved it both. So if you move it between both, you can do that and get the right answer. So see here, we multiplied the divisor basically by 100. That's my justification for how I came up with it. And then you're just going to divide like normal. Some tools for being able to do this as mental math exercises would be breaking and bridging. So I would look at 1.5 and 3.7, and I'd say, well, that's pretty much 1.5 plus 3, give or take. And then I could look at 4.5 plus 7. I could look at, well, 4.5 plus 7 is roughly 5.2. And I could keep building from that. So we're kind of using an estimation system here to get there a little bit quickly, and we're breaking it down piece by piece. If I want to look at compatible numbers, decimal numbers are compatible when their sum is a whole number. So when I'm adding 4 decimals together, I could say, well, if I add the first and the third number, then I'm going to get a whole value. So I'm going to have 4.09 plus 7.91, and that's going to be 12. So I might want to add those two first, and then I can roughly add 3.875 and 0.15 because they're 4. And then I can add those together to get a whole number. This doesn't happen very often unless we're dealing with like money. A lot of times when we're paying for things in money, we've got quarters, 50 cents, 75 cents. Those are easy to see. If I want to force compatible numbers, I can sort of round things off. So 9.27 is basically 9.25 plus 0.02. And then I know that 3.79 is 3.75 plus 0.04. Why on earth will we want to do this? We want to show our students how to estimate, and this is kind of like rounding up to the nearest whole number to be able to combine things. The best way to do compatible numbers is to round it to the 10th place, or it's going to be to do it in increments of 0.25. That's kind of how you want to teach your students to use the strategies. You would use it when we could round to the 10th place, or we could get to increments of 25. The same thing happens when I'm subtracting. I can do that same breakdown to force a whole number and to get my final answer. Now, if I want to balance with decimals in division, I know that if I take 0.25, I could move the decimal 2 places to the right. That's absolutely could happen. But I know that if I just multiply it by 4, 0.25 times 4 is 1. So that's a strategy you could use here because you've got a quarter basically. Rounding can be done on some calculators using the fixed key. This is for your advanced students. You definitely don't want to show your beginner students how to do this, but you can have it round to certain decimal places. So if I enter the decimal 2.3669, I can tell it fix 3, and the display will show me the value to the third decimal place. When I hit equal, it will actually give me the rounded value. So at first you kind of have this like, uh-oh, did I do it wrong? Because it shows up with zeros. But then you hit equal and you'll be able to see what it actually is. So if I want to round the following numbers, I'm not going to take the time to explain each one of these because we should be pretty familiar with our place values. Remember that your rounding rule is if it's 5 or greater, you can go up. If it's less than 5, you're going to round down. If I want to estimate decimal calculations using that rounding, I just need to be careful that you're remembering how much you're rounding in reference to what you have. So you don't want to be rounding entire dollar amounts if you're dealing with decimals because then you could wind up way off of the actual value. So if I'm looking at round off errors, I'm looking at non-zero digits are always significant digits. If it's any number other than 0, it has to be significant. Zeros before a digit are non-significant, so they don't matter in the grand term of things for rounding. Zeros between other digits are significant. Zeros to the right of a decimal point are significant. And zeros at the end of a number, this is where they're not significant, only if there is a decimal point there. So if there's not a decimal, the zeros at the end of a number don't count for significance.